Hi, I'm Peter Smallage. I'm the director of the Cornell University Arnot Teaching and Research Forest. It's my pleasure today to host the 2012 presentations of the Undergraduate Research Intern Program. This presentation is going to be by Seth Lutter. Seth is a student in the Department of Natural Resources in the College of Agriculture and Life Sciences. Seth will be talking about microclimate effects in retained wood on the forest floor. So let me open Seth's presentation, and then I'll turn the presenter status to Seth. All right, Seth, welcome, and the floor is yours.
Thank you for the introduction, Pete. I'm going to talk today about the benefits of leaving woody material on the forest floor. My co-authors for this project were Steve Moriali and Christy Sullivan. Before I start, I'd like to thank Kathy Garcia and Devin McMahon, my fellow interns this past summer, and the staff at the Arnot, Gary Goff, Kathy Coates, and Peter Smallage for their help this summer. So last winter, the price of oil hit $100 a barrel for the first time since the 2008 recession. As prices continue to rise, people will look elsewhere for energy sources. So sources like wind, solar power, or biofuels. In New York State, our forests can provide abundant and renewable source of biofuels. The map in the lower left shows that New York State today is 2/3 forested. So during traditional forest management, the main stem of a tree is taken out, and the tree top, the smaller branches at the top of the tree, is commonly left behind. This material is being labeled by the industry as waste and can be used for biofuels, so to produce heat or electricity. But could there be negative consequences of removing this material from our forests? And could there be a tipping point at which removing this material is no longer ecologically sustainable? So our project, we wanted to look at the possible benefits of leaving woody material behind. And so to quantify the effects of woody material on the forest floor, there are lots of different ways that you can measure these effects, such as salamander abundance, which Devin talked about, soil nutrients, soil invertebrates, forest regeneration, and the topic of my project, forest floor microclimate. So my objective was to determine whether piles of woody material can increase environmental complexity by altering the forest floor microclimate. There are many different components of microclimate, and the two that I measured were soil moisture and temperature at ground level. So for our project, we have 3 different treatments of woody material removal. The first, in the upper left-hand corner, is the 10-inch diameter treatment, where material 10 inches or less in diameter was left on the forest floor. The second treatment is the 4-inch diameter treatment, which is a medium removal, in which material 4 inches or less in diameter was left on the forest floor. And the final treatment is the whole tree removal treatment, in which whole trees were taken out. These 3 different treatments were replicated at 3 different study sites, at the Arnot and at Mount Pleasant in Dryden. So each of these treatments is a 1.5 hectare plot, and this diagram shows that within the 10-inch and 4-inch treatments, where woody material was left on the ground, the woody material was put into piles that were distributed across the landscape. and this is very important for the measurements that I made. So this slide shows a different way of looking at the 4-inch and 10-inch treatment. The 4-inch is the smaller branches at the very top of the tree, and the 10-inch treatment leaves a considerably larger amount of the tree behind, so larger branches and maybe even parts of the trunk. So to measure temperature, we used hobo data loggers, which were deployed from the end of June until the end of September. The data loggers were embedded into PVC pipes so that they weren't measuring they were being protected from solar radiation, and they were suspended a few inches off the ground so that they were not being affected by heat conduction from the soil. We had 96 total data loggers deployed, and the reason I have 2 data loggers in this picture are because each data logger had a pair. In the 4-inch and 10-inch treatments, the pairs of data loggers were in pile and open pairs. So every pile had an open site associated with it, which was 5 meters, roughly 5 meters away. In the whole tree treatment, the data loggers were still paired, but since all of the woody material was removed, there were no piles on the ground. So there were 96 total data loggers, which translates to 32 per treatment. And also the data loggers recorded for every 4 hours, which is important. I also measured soil moisture in percent volumetric water content. So these pictures show me measuring soil moisture at a pair of a pile and its paired open site, which is roughly 5 meters away. I took a total of 342 samples, which translates to 171 pairs of samples. And I only took volumetric water content measurements in the 10-inch and 4-inch treatments because I was looking at the effects that piles might have on soil moisture. There's a lot of variability within each pile, and so when I measured soil moisture, I would measure it at the densest part of a pile, which would be somewhere over here on the right-hand side, and a medium density part of the pile, which would be somewhere over here on the left-hand side. So getting into our results, this graph shows a pair of the 96 data loggers that we put out. So the temperatures that they logged are graphed over the course of the summer, and the open data logger is in red, and the data logger which was in the pile is in black. So the 2 things I want to point out about this graph are that, okay, so in this graph you can see daily variability, you can see daily fluctuations in temperature, and you can also see a seasonal trend as temperatures decrease towards the fall. So the 2 things I want to point out about this graph are that the daily variability in open sites is much higher, and that this is because the high temperature peaks in open sites are much greater. So there's a lot of different ways that you can analyze data like that. So, and we decided to look at the temperature variance and the maximum temperatures. So these box plots are of the seasonal temperature variance for pile and open data loggers. So there's 32 in each of these groups, 32 loggers in each of these groups, with a single variance value calculated for each logger. for the entire course of the season. And so we were able to do a paired t-test because each data logger in a pile has a pair in the open, and the paired t-test was significant at the alpha equals 0.05 level. So this means that the open sites experience significantly more temperature variance than their paired pile. We were also interested in looking at temperature across treatments, and so this graph shows the 3 different treatments on the x-axis and variance on the y. So in order to compare across treatments, we had to look at only open sites because the whole tree removal treatment doesn't have piles. So what you see here is a secondary or tertiary effect that the piles or the treatment might have, because the 10-inch open sites, not piles, open sites in the 10-inch treatment have less variance than open sites in the whole tree removal treatment. So we did a Kruskal-Wallis one-way analysis of variance, and the p-value was 0.054, which means that at least one of these populations was significantly different than the other two. So we looked at temperature variance. We also wanted to look at daytime temperature extremes, which are circled here. And so we decided to look at temperatures exceeding 30 degrees Celsius. So 30 degrees Celsius is pretty hot for some organisms. 35 degrees is an upper limit for red-backed salamanders, which are very common in our forests. And so we did a paired t-test between pile and open sites and found that open sites experienced temperatures greater than 30 degrees Celsius significantly more times than their paired pile. This means that organisms in open sites are experiencing greater temperatures at a greater frequency than an organism in a pile 5 meters away. So remember, I also measured soil moisture, and remember that I did this again with paired samples. So this graph shows a week in the life of a pile and its paired open site during the first week of August. So the rain events are in blue, are the blue vertical lines, and volumetric water content, which is measured in a %, is on the y-axis. So at the beginning of this week, the open site had roughly 7% water content, and its paired pile had 15% water content, which is double. So the pile had double the water content of its paired open site. And this difference was retained for the entire week. So not every pile and open relationship that we found was as clear-cut as this one, but we did a paired t-test on 171 pairs of these data points, and we found that piles at this site were significantly wetter than their paired open. So, piles of woody material on the forest floor can reduce temperature variability, can reduce high temperature extremes, can increase soil moisture and retention in drier sites and during droughts, and this has implications for climate change. As temperatures rise and precipitation becomes more variable, piles of woody material can increase environmental complexity, provide refuge for organisms, buffer temperature and moisture extremes, and increase resilience of our forest ecosystem. Thank you very much for your time. And that's all.
Great job, Seth. Thank you. And I hope that you have a good end to your semester here with finals, and I want to thank you for being part of the Arnot Intern program this year.
Thanks, Pete.